This is the Limb Remover 6000. Don't look at that. It spins this 40-pound tube up to 1,000 RPM to coat the inside in mystery goo. This stuff is under 100 Gs of acceleration to get an even distribution. The tube is the case for my Space Shot solid rocket motor, and the mystery goo is a thermal liner that protects it from melting during the burn. I dialed in the formula for this stuff last summer, but as you'll see in this video, it still needs some work, and that's not the only problem. Between 3D prints that got too hot, a mixer that went too fast, and a machine that desperately needs some thread locker, this spin casting problem was harder to solve than I thought.
Oh yeah, dude, I think this is not good.
The Limb Remover 6000 is made from 1515 aluminum extrusion set up in a frame. Two caster wheels are placed at either end to support tubes of any diameter. The tube is constrained at either end with casters running along the edges and constrained vertically by casters at the top. These are loosely engaged to prevent this thing from bouncing out and unleashing about 1,000 joules of kinetic energy. That's about the same energy as someone throwing a gallon of milk at you at 50 miles per hour. You'd probably survive, but it would be upsetting. The tube is spun by an O-ring geared down and connected to a CNC spindle motor that drives it. This lets me change the speed using the spindle controller. As you'll see later in this video, we actually need to coat the tube in several liquids at various speeds. Spinning a tube for long periods of time at variable speeds is something only a spin caster can do. There is no other machine that can do this. But like, for real, why not use a lathe? These things are designed to spin heavy objects for long periods of time, and I know it could work for spin casting because I've done it. When I made the Simplex V2 motor last year, I spun cast the liner on this, and it worked great, so why would we switch it up now? The main reason is that I now mix and cast rocket motors in a new space that I'm calling the bakery. I set this place up recently, and the goal of it is to keep the dangerous parts of mixing and casting rocket motors in a controlled, isolated area. This space is not a machine shop, it's not for fabricating parts, it has one goal: keep the hazardous operations in a controlled, designated, isolated area. So I'm not gonna move the lathe here, and it isn't very close by. When I mix a liner, the last step is to add the MDI, which hardens the mix in a matter of minutes. That means I can't mix a liner in the bakery, then bring it to the lathe to spin cast. It'll take too long. If I wanted to use the lathe, I'd need a mixer right there. But you need more than a mixer to make a liner. You need HTPB, IDP, MDI, carbon black, Kevlar pulp, mold release, etc. Most of these are the chemicals that I use to make rocket motors, and they all belong in the bakery. It's a huge waste if I have to store two sets of materials in different places. So, I cannot use this lathe, I need a separate spin casting machine. My first step was to hit up my buddy Sam Austin. Sam had built a spin caster previously for 4-inch motors out of steel unistrut, some soft rubber wheels, and an Arduino for speed control. He wasn't using it, so he shipped me the parts and I got it set up. I like to show the parts of a project that make me look good, but it's worth showing the parts that make me look dumb. And this one is the latter. I don't know why it didn't click for me that an 8-inch tube wouldn't work on a 4-inch spin caster, but it didn't. And the diameter isn't the issue, it's the mass. At a guess, the tubes that Sam was working with here were probably 13 pounds, and with the liner loaded, my case will be 50. While Sam's design did spin the tube, the soft rubber casters started rubbing off on their mounts. The motor couldn't spin it very fast, and to make this feel safer, it needed enough modifications that I decided to start from scratch. I picked aluminum T-slot extrusion because I've worked with it so many times before, and it's basically like Legos for engineers. I guess that's just Legos. It's like expensive Legos for engineers. Okay, it's still just Legos. It's like really expensive Legos for An important part of this design is thread locker, i.e. the stuff you should be applying to every single screw on a machine that vibrates. I'm not putting any of that on at this stage. The goal right now is to make sure I know where each joint needs to go, and once that's done, we can lock everything in place. That's why this goofy clip of an early on test has screws falling out. I thought it could be fun for us to take a vacation to the island here, but I think this was a funnier bit in my head, if I'm to be honest. I need to make sure this spinning tube can't become a flying tube. There are two main ways that can happen. The most obvious of these is the tube bouncing up off of the 4 base rollers. If the liner has any asymmetry, this is bound to happen. Tubes only do this when they're really unhappy. To prevent it from bouncing up and out, I put a single roller on top between the two base rollers. Provided the tube is straight, this should keep it from bouncing around in the machine. Weird that it doesn't seem to be working though. Seems like you could just move the roller down a little bit and constrain it harder. Huh. Wonder if there's an explanation for that requires context we haven't yet learned. The second vector of destruction is the tube scooting out either side of the machine. Unless the tube is a perfect circle, it's not. And unless the rollers are perfectly aligned, they aren't. The tube is naturally going to want to slowly move to one side or the other. I constrained this with an elevated roller on either side that can roll against the edge of the tube. And that's how I keep this setup just a little bit safer. All right, let's leave the island. This place sucks. I wish I was in bed scrolling reels. I picked a CNC spindle motor to drive the tube for one simple reason. Shipped way faster than everything else. There's a good argument for it though. On a fundamental level, this is a motor that's designed to spin for long periods of time, and it comes with its own mounting points that slot right into T-slot hardware. It's also air-cooled with its own internal fan, which keeps the setup much simpler, but as for speed, it maxes out at 24,000 RPM. That's way faster than I need. As a fun thought experiment, if I managed to spin this tube up to 24,000 RPM, the G-force on the internal surface would be irrelevant because the hoop stress within the tube would have caused it to explode. Cool! By gearing the motor down, I can target something more reasonable. I 3D printed a 2-inch O-ring drive wheel to attach it to the CNC spindle motor, and an 8-inch tube with a 2-inch drive wheel is a gear ratio of 4:1, so our max RPM, hypothetically, is now 6,000 RPM, which of course we're not gonna hit. The friction from the wheels, the shape of the tube, and the low torque from a CNC spindle means we're probably gonna fall well short of that number. In experimental testing at home, I was able to hit about 1,000 RPM on the case alone. That felt like a nice round number, so with the location of the joints all set, I applied a generous amount of thread locker to every critical screw. After running the Spincaster for about an hour, I got out a thermal camera to make sure nothing was overheating. The motor was by far the hottest, at 100 degrees Fahrenheit or 39 Celsius. For a full hour of running, this doesn't feel too bad. The O-ring and base rollers only got mildly warm. The way this camera scales colors is a little deceiving. This wheel looks very hot, but it's actually only 27 Celsius, which is 80 Fahrenheit. All these numbers sound fine to me, so I put the Spincaster in my car and started driving to the bakery. While I'm heading to the bakery, let's talk hypotheticals. This drive wheel is made out of PLA plastic, so it melts at low temperature. Hypothetically, if this were to experience a bunch of friction, possibly hypothetically, it could get hot. That could, in theory, perhaps lead to a problem. If you were smarter than me, you might solve this problem by getting this part CNC machined by the sponsor of today's video, PCBWay. Don't let the name fool you. PCBWay certainly does circuit board fabrication and assembly, but they do a lot more than that. Metal machining is something that takes me a lot of time, and it's not just because I'm bad at it, it's because I have a lot of parts to make. If I were to make all of those parts myself, it would take me forever to finish a project. With the ability to upload a part file, get a quote, and get that part made, PCBWay makes it very easy to reach the finish line on your projects. Someone should make a video about reaching the finish line on your projects. Hypothetically, this part would have been a great candidate to get made by PCBWay's machining services. And not to spoil it, but if I had planned a little further ahead, I probably would have done that. Maybe you don't have access to a big fancy machine shop, or maybe you simply don't have the time to spare to make every part on your project. And for either of those scenarios, PCBWay is a great fit. And they offer even more services. You can do sheet metal fabrication, injection molding, all sorts of 3D printing, and more. I've worked with PCBWay before on things like the copper tip for the meat rocket, and their service is very easy to use. If you want to give PCBWay a shot, you can do that using the code on screen or the link in the description below. Thanks so much to PCBWay for sponsoring this video. I really wish I had used their services for this part, and you're gonna find out why in just a few minutes. I mixed a batch of Mystery Goo liner on high speed for about 10 minutes with the curative in. At over 60%, the bulk of this liner is made of hydroxyl-terminated polybutadiene, which is just a fancy way of saying liquid rubber. If you watched this video, you know that Kevlar pulp is also an important ingredient in this mix. The pulp enhances the performance of the liner during the burn. The two main upsides are that it pyrolyzes well, meaning it helps the liner form a char layer, and the stringiness of the pulp helps keep that char layer attached to the wall, instead of getting ripped away by the solid motor exhaust. The downside is that it nukes the flow properties of the liner. It becomes a very thick sludge, like thick with 5 C's, so getting it to spread out is not easy. Ideally, I could simply pour the liquid liner out of the mix bowl into the motor tube and spin the tube until it's even, That's how spin casting is supposed to work. The intense G-loading around the edge should spread a liquid out evenly, but mystery goo is so bad at flowing that we need to dispense it reasonably close to where it needs to end up. With the curative added in, the clock is ticking until this stuff hardens. I poured it into a long length of PVC tube with the help of my buddy Cam, who did not know how much manual labor he was signing up for. At this scale, it's simply way too much work to do this stuff alone, and I'm really grateful to have friends who are always down to help. Thank you, Cam. This pipe is going to be a liner dispenser. It's essentially one long cock tube. In previous motors, I've used smaller individual cock tubes, but those cock tubes are not big enough, and since they're small cock tubes, you need like 6 or 7 cock tubes to make it work. Please forgive me, I have the humor of a 10-year-old. Using Onshape, I designed this nifty way to get an even coat along the inner surface. We've got a tube, a nozzle, plunger, piston head, handle, and rollers. The rollers allow the tube to slowly spin while the dispenser rests on the inner surface. The outer tube is filled with mystery goo, and as it's pulled back against the anchored piston head, the goo is dispensed out the nozzle. Since the tube is slowly spinning and the nozzle keeps moving back, in theory, we should get an even coat of goo spiraling along the inner surface. But as soon as we began, the problem started showing up. Rotating at the slowest constant speed I could, Cam anchored the plunger and started pulling the outer tube back. Instead of sticking to the inner surface on the case like I wanted, the liner would bunch up into segments. It was much easier for it to clump up and stick to itself rather than form a new bond with the case. Once it did stick to the case wall, that only made it easier for clumpy sections to form. At the same time, we started hitting air pockets within the outer tube. In my stress to get liner loaded into the dispenser before it started to harden, I had inadvertently created big air pockets within it. Pockets ruin the whole goal of this tube setup, which is to ensure even distribution along the length of the case. The dispenser is sized for the target thickness of the liner. That means the cross-sectional area of the dispenser tube matches the cross-sectional area of the liner. Even if we don't get a perfect distribution radially on the inner diameter of the tube, we still get a good distribution along the length of the tube because those cross-sectional areas match. But air pockets in the dispenser will ruin that whole equation. If we distribute liner unevenly along the length of the motor, spin casting will help, but not by much. The liner doesn't flow well enough for us to count on that. Cam and I did our best to coat as much of the inner diameter as we could, but the problems only got worse. After distributing the liner along the length of the tube, I made the critical mistake of letting it sit for a few minutes while I inspected the inside to see how well it had coated the ID. While it sat, a good portion of the liner slumped to one side, making the radial distribution even worse, and when I tried to spin it up to full speed, the tube started slamming around because of the asymmetry. That slamming action took enough energy out of the system that it could never get faster than this speed, which is not really fast enough to do what we want. We tried our best to adjust the top roller on the machine to keep the tube from slamming around, but when the wheel was fully engaged, there wasn't enough motor power to spin it fast. After a few attempts like this, I decided to throw in the towel. The slamming tube does not bode well for the safety of the situation, but it wouldn't even matter if we kept spinning it, because the liner had started to harden by this point. At the start of the liner curative cycle, the mix was about 80 degrees Fahrenheit, but after only 10 minutes of mixing on high speed, it had shot up to 105. I mixed on high instead of low or medium to try and buy back time for me to load liner into the dispenser, but had actually shot myself in the foot. The elevated temperature made the liner cure much faster than normal. This dramatically shortened the work life of the liner, so effectively, we were cooked before we even loaded it into the case. Unfortunately, this case is scrapped. The liner has a very strong bond with the inside wall, and it won't be worth the effort to peel it off. The strong bond is a good thing, and it's intentional. I chemically etch and conversion coat the inner diameter of the case before we spin cast the liner into it. This makes the bond between the liner and aluminum way stronger than normal, and it will help keep things attached under high G loads during flight. But since this tube is scrapped, the next day I called a local metal supplier who said they could have a new one of these ready by noon. So while I'm driving to get a new case, let's make some changes and fix some problems. Problem 1, the CNC spindle motor does not have enough power. The solution? Add a second one. I'm not even kidding, it just makes sense. I know the motor works, it just lacks power. I picked it because it was cheap, shipped fast, had existing mounting holes, and an existing cooling setup. I also didn't need to spend any time messing with electronics. I took the motor out of the box, plugged it in, and it worked. Plus, with two motors, if one of these guys dies during casting, we can just fail over to the second one. This is the exact same reason I mix with two small propellant mixers instead of one large one. It's just nice to have a little more redundancy for a task where everything has to go right each time. Problem 2, engaging the top support makes the tube bind up in the center. I'll fix this by adding a second top support. These tubes aren't always perfectly straight, so by adding a second wheel, we keep the points of constraint at 2 locations. In a hypothetical extreme, if this tube were a banana, it could still rotate freely. Problem 3, air bubbles in the dispenser. The solution to this is a funnel. The liner needs to slowly drip down the center of the tube without touching the side. That's how those bubbles form in the first place. The funnel lets liner drip through this center hole and has vents to let the displaced air leave the tube. Problem 4, the dispenser itself doesn't work. This issue stems from the liner gently falling onto the wall and not sticking on the ID of the case. So instead of letting it fall onto the wall, let's just squish it directly on in the first place. And instead of spinning the case while it's dispensed, let's leave it stationary and squish the liner onto opposite walls to try and keep some symmetry. Finally, problem 5 is that the liner cures too fast. This one's an easy fix. I flew too close to the sun by mixing on high speed when we were prepping the first liner. The high speed created too much friction in the mix, which shot the temperature up and accelerated the curing process. I'll dial it back by mixing in the curative slowly, which will keep the temperature down, which will help the liner flow for longer. With all these problems fixed, let's get a new case.
Howdy! Put it in the trunk here. Alright, that'll do it. This is perfect. You guys are saving my bacon.
Oh yeah?
It's almost the weekend and I needed this too.
Rocket?
Yeah.
I don't think this guy recognized me, but he immediately clocked that I was making a rocket motor. I brought the new case home, cut it to length, polished it up, drilled the radial bolt holes for the forward closure and the nozzle, and within a matter of hours, we are ready to go again. Before casting a new liner, I took the old ruin case and tossed it on the upgraded spin casting machine, then sent it as fast as I could. I was able to get the lopsided liner tube up to 700 RPM, which should make the liner on the inside wall experience about 50 G. And we should be able to get those numbers a lot higher when the liner isn't asymmetric. So let's try it. Before mixing and casting anything, I used the spin caster to re-etch and reconvert the inside of the case to promote liner adhesion. I'll probably get into this in another video, but this stuff is nasty and it will mess you up if you're not careful. The best chemicals for rockets seem to be the worst for human health. With the case etched and prepped, let's make a new liner. I'm tempted to change the formula of the liner, but that's a topic for a future video. I do actually think there's a lot I can improve in this formula and get a similar performance while lowering viscosity and making it spread more easily. If you want to see those experiments, make sure you're subscribed. We set up a tarp on the ground and a ton of sandbags around the spin caster, then loaded curative into the mix. Going on low speed with lots of scrape downs, we kept the temperature low, then began loading liner in 1 cup at a time to the funnel. This did not work great on its own. The flow wasn't nearly fast enough because the hole in the center was too small, but I was able to force it through by pushing it down with my hands.
Oh, dude, it's like Play-Doh.
Massaging a warm, semi-liquid substance with my hands into a tube was one of the experiences of all time, but it did work. We tracked the mass of liner getting loaded into the dispenser with a scale to ensure there weren't hidden air pockets like last time, and then we loaded the dispenser into the case and started pushing. The dual nozzles on the end of the dispenser worked exactly as planned, squeezing the liner up against the case wall on opposite sides. The whole dispensing time took about 2 minutes, then we rotated the tube upside down for another minute or so. Obviously, the liquid liner slumps down the sidewalls a bit, so by letting it hang upside down, my aim was to keep the distribution symmetrical. Once it had settled a bit, I cranked up both motors and started spinning. It only took 15 minutes to get the entire inner diameter coated, and although I had to reach in and patch 1 or 2 spots with some extra liner, all in all, this attempt went much smoother than last time. Shortly after this, I noticed one of the O-rings driving the case had fallen off, but it turns out it wasn't just the O-ring, it was the 3D printed drive wheel. I shouldn't be surprised by this, but CNC spindle motors get hot, and that heat doesn't do very nice things to a 3D printed plastic part. Thankfully, it only happened to one motor, so I was able to fail over to the other one and keep the tube spinning as designed. This is something we'll need to improve before making another motor. The case and liner were spun for about 3 hours while the liner cured, and after it had hardened, we removed the end caps. The internal surface had a beautiful rough texture which will help propellant bind to it, and apart from a few sections which came out thinner than I had hoped, this liner passes. And like, demonstrably, it passes. Super 8 burned for 12 seconds, and the case remained cool enough to briefly touch just a few minutes after. For 12 seconds of motor exhaust that burns at thousands of degrees no matter which units you're using, that's pretty good. As for the spin caster, this thing still needs work. While it limped across the finish line for this motor, there are some obvious improvements needed. The dual motor CNC spindle setup is okay, but generally lacks torque. The O-ring drive wheels obviously need to be machined from aluminum if they're going to hold up in the future, and I'll want to keep checking on those wheel bearings. They did fine, but I'd expect them to fail at some point. There's a lot of spinning going on. As for the liner mixture, this needs work too. I really don't want to drop the Kevlar content, but this stuff doesn't flow well enough. More than likely, we can improve the pourability by adding surfactant. I haven't done any of this yet, and all of these upgrades deserve their own video, so watch for that in the future. I've got another video about this motor coming real soon, but if you're impatient like me and you just can't wait, I post updates every 2 weeks on Patreon about what I'm working on. That's how this project is funded, and I'm so grateful to the folks who support over there. And I'm grateful to you for watching. My name is Joe Barnard. May your skies be blue and your winds be low. Aga bye.